Hello everyone. In this video we look at introduction to one of the important phenomena in physics, which is collisions. Now, what is a collision? A collision is seen as an isolated event where the effect of the external forces is supposed to be insignificant, where we can take that the external force acting on the particles involved in the collision is insignificant, and the collision will involve a strong force acting between the particles or the bodies which are participating in the collision for a very short time, and this force is what we call as the collision force or the mutual interaction force. As a result of this particular force that is operating during the time of collision, the energy and momentum values of the particle which is participating in the collision, so we are looking at each and every particle separately, will be undergoing a change, and this phenomena is what we call as collision. Now when we talk about collision, the general perception is that the particles or the bodies involved in collision may actually have a physical contact, which is not completely true, because only in some collisions, like the collision between the billiard balls and collision between the ball and bat while we are playing cricket, only in these type of collisions there will be a real physical contact or real touch between the particles. Whereas when we look at collisions between charged particles, like in the case of collision of an alpha particle with the nucleus, like alpha particle is helium 2 plus ion, which is positively charged, and nucleus is also positively charged. So when the alpha particle is approaching the nucleus, the alpha particle will start getting deviated even before it makes a physical contact with the nucleus. So such type of collisions, we may not have a real physical contact between the particles involved in the collision. Now when we talk about the collision, we'll mainly look at one category of collisions which we call as simultaneous collisions. So simultaneous collisions would mean that the particles, maybe 2 or 3 or 4 or 5, whatever, they will be having interaction together. So which would mean that the particles, whatever be the number, it will be always definitely more than 2. When they are undergoing the collision phenomena, it will be a mutual collision that they will have, where in one step all the particles would see a change in the momentum values or the energy values, and once this is happening, we would see that the particles will be having a change in their direction of motion and even sometimes the speed of motion. So such a phenomena is what we call as simultaneous collision. Now the other type of collision which can be studied is successive collision. Let us say, for example, we have particle 1 and particle 2. First the particle 1 and 2 are colliding, and then the particle 2 would go and collide with particle 3, and maybe then the particle 3 might go and collide with particle 4. So such type of collisions which happen in steps, we call them as successive collisions. In our study we are going to be limiting ourselves to these simultaneous collisions. Now when we look at the collision process as a whole, we can divide this into 3 stages. The 3 distinct and identified stages of collision are one, the phase before the collision, where the particles will be approaching each other, and the second stage is during the collision time, and the third stage where the particles will be receding from each other. So there are these 3 stages: one before the collision, during the collision, and after the collision. Now in the before the collision stage and after the collision stage, the interaction forces which we talked about will not be operating, which means the interaction forces will be 0. But during the collision time, which is in between these 2 stages, the interaction forces are going to be operating. Now the interaction forces which are responsible for the collision process will be very large in terms of value. The reason being, the collision time will be very less, and if you look at the force acting on any particle as a rate of change of momentum, then since the time value is very small, we would see that the value of these interaction forces would come to be very high. And of course it is not quite possible to find what is the value of these interacting forces, and hence in this case we will not be able to apply the Newton's second law. Only when we know the force we will be able to apply what is the resulting impact of the force in terms of the acceleration or the change in momentum of the particle. Now when we talk about the collision as a phenomena, the external forces such as gravity or friction, we will not be taking them into account, for the simple reason that even if they are present, since the collision time is very small, the change in momentum by the time taken value will be substantially high, and this impulsive force is mainly because of the interaction between the particles, and since this value is going to be very large, we may neglect the effect of the external forces such as gravity and friction. And thus if we look at the system of particles involved in the collision process, if there is no external force, as we previously discussed, if the external force is 0, then the total momentum of this system, so if you look at the momentum of all the particles involved in the collision before the collision stage, that would be same as the total momentum of particles after the collision. The individual particles may change their momentum values, but the overall momentum of the system will remain unchanged. So a collision will satisfy the law of conservation of momentum. Similarly, if we look at collision as an isolated phenomena where there is no effect of the external forces, then the total energy of the system also must be conserved, because energy can neither be created nor be destroyed. When we talk about the energy, please keep one thing in mind, that we are not just referring to the kinetic energy of the particles, we are referring to the total mechanical energy, we are referring to the internal energy, we are referring to the excitation energy, means the electrons of the particles may get excited, the nucleus of the particles may get excited, we are referring to the radiant energy, some energy might be getting radiated, and even we are looking at the energy that could be converted into the mass, because Einstein's equivalence relation E is equal to mc square talks about how energy can be converted into mass and how mass can be converted into equivalent energy, where the idea is if you have a mass m and we change this into energy form, the equivalent energy value will be given by E is equal to m times c square, where c represents the speed of light. So if you take all these forms of energy into consideration, then the total energy of the system which is undergoing the collision before will be equal to total energy of the system which is thereafter. So here we are not just referring to just the kinetic energy values, we are representing all the different types of energies that are going to be existing. So a collision should also satisfy the conservation of energy. Now we just look at a sample illustration which will explain the application of conservation of momentum. Two particles 1 kg and 2 kg undergo collision, with 1 kg having initial velocity of I plus 2j plus k meters per second. So here the mass is given in SI unit and even the velocity is given in SI unit, and the final velocity is 2I minus j plus k meters per second. What is the final velocity of the 2 kg particle if it has initial velocity of I minus j meters per second? So we have two particles here participating in the collision. Let us say the first particle is having mass m1 which is equal to 1 kg, and the second particle, let us represent this as m2, the mass is 2 kg. The initial velocity of the first particle, so since velocity is a vector, we will represent this as u1 bar, will be I plus 2j plus k meters per second, and the final velocity after the collision for the first particle, let us represent this as v1 bar, will be equal to 2I minus j minus k meters per second. Now the initial velocity of the 2 kg particle is given as I minus j, so we are representing this as u2 bar. the final velocity of the 2 kg particle after the collision is unknown. Now when we look at collision process, the total momentum of the particles before the collision must be equal to the total momentum of the particles after the collision, which means the total momentum of particles before the collision will be m1 u1 bar plus m2 u2 bar. Because momentum is a vector, we have to add these quantities like the way we add vectors, is equal to m1 v1 bar plus m2 v2 bar. Now m1 is 1 kg. Since all of them are already in the SI unit, we will omit the use of units, and we know the final value of v2 will be coming in the unit of meters per second, because everything is already taken in the SI system. So m1 is 1 kg, so we'll straight away keep just the values. 1 into u1 is I plus 2j plus k. m2 is 2 kg, so 2 into u2 is I minus j is equal to m1 v1 bar, which is 1 into 2i minus j minus k plus 2 into the v2 bar. This v2 bar is what we are trying to find. Now on the LHS side, if you look at it, there is 1 into I is I, 2 into I is 2i, so totally it will be 3i, 1 into 2j is 2j, and 2 into minus j will be minus 2j, so both of them will be cancelling, and 1 into k will be k. This is what we have on the LHS, is equal to 1 into 2i is 2i, and 1 into minus j is minus j, 1 into minus k is minus k. So we are looking to calculate the value of v2, so we will take all the other terms to the LHS. So whatever is plus on the RHS will become minus. So what we would have, I'm just writing it over here, is 3i plus k. Now when we bring 2i to the LHS, it will become minus 2i. When we bring minus j to the LHS, it will become plus j. When we bring minus k to the LHS, it will become plus k, is equal to 2 times the v2 bar. So 3i minus 2i, it will be I, and we have just j, k plus k, it will be 2k. So this is 2 v2 bar. So we are looking for v2 bar, so v2 bar will be equal to, when we bring the 2 to the LHS, it will be coming into the denominator, so it will be I plus j plus 2k whole divided by 2. The unit is going to be meters per second. I mean, we can even write it as half I plus half j plus k meters per second. So this will be the final velocity of the 2 kg particle. So whenever we are looking at the collision phenomena, the total momentum of particles before the collision must be equal to the total momentum of the particles after the collision. Now when we look at the collision between two particles, because this is an important situation or a scenario rather that we'll try to analyze in terms of collision. Collision might involve more than two particles also. If you have collision of just two particles, let us say we have particle 1 of mass m1 and particle 2 of mass m2. Let the initial velocity of this be u1 bar and the initial velocity of this be u2 bar. Now velocities may be in different directions. The final velocity of particle 1, let it be v1 bar, and final velocity of this, let it be v2 bar. Now like the way we try to analyze the motion of one particle with respect to other particle in kinematics, if we try to observe the motion of second particle with respect to first particle, the relative velocity of the second particle with respect to first particle before the collision will be u2 bar minus u1 bar. Same time, the relative velocity of the second particle with respect to first particle after the collision will be v2 bar minus v1 bar. So these are the relative velocities of the second particle with respect to first particle. This is before the collision, and this will be after the collision. Now when we look at with respect to the first particle, before the collision it will appear as if the m2 particle is approaching. After the collision it will appear as if the m2 is receding. So the ratio of just the magnitudes of the relative velocity of separation. So why we are calling as separation is because after the collision it will appear as if m2 is getting separated from m1 to the ratio of relative velocity of approach before the collision. We are keeping a modulus value so that we will just look at the magnitude. This ratio is defined as coefficient of restitution. Now the coefficient of restitution, when we go to the specific examples of types of collision, this will have a role to play. So we will be able to differentiate between the types of collisions by looking at the values of this E. So coefficient of restitution is defined as relative velocity of separation after collision. Relative velocity of separation after collision divided by the relative velocity of approach before the collision. And this will have significance only when we are talking about the collision between two particles. When we look at the collisions, we can divide collisions into different categories, and first classification is based on the aspect of kinetic energy of particles involved in the collision. Now when we look at the kinetic energy of the particles, when the particles are undergoing the collision phenomena, the particles would be coming together. We are looking at the collision of two particles. When the collision is occurring, the particles would be pressing one against each other. So what would happen is, some of the kinetic energy of the particles will be changing into the elastic energy. And in some collisions, what would happen is, as the particles are receding back, the elastic energy will be fully getting converted into kinetic energy form. Maybe that the individual particles might see a change in the kinetic energy value, but the overall energy of the particles involved, if it is remaining constant, then such a collision is what we call as perfectly elastic collision. It is a collision in which the kinetic energy after the collision is equal to kinetic energy before the collision. So when we say kinetic energy, we are looking at the total kinetic energy of all the particles, and such a collision we call it as perfectly elastic collision. So in a perfectly elastic collision, the total kinetic energy of all the particles after the collision will be equal to total kinetic energy of all the particles before the collision. And generally, we have very few examples of such collisions. The collision between atomic particles, collisions of gas molecules, between the gas molecules as well as with the walls of the container. So in such cases, we see that the kinetic energy will not be lost by the particles. So such collisions we call them as perfectly elastic collisions. The other side of the story is where we see that the kinetic energy after the collision is not equal to kinetic energy before the collision, and in such a case we call it as inelastic collision. Now generally, the inelastic collisions will have kinetic energy final less than kinetic energy initial, where the energy lost will be converting into the form of heat, sound, maybe the elastic energy of the deformation or excitation, and so on, sometimes even light. So these type of inelastic collisions, we see that the final kinetic energy value will be less than the initial kinetic energy. And we also have cases where the final kinetic energy may be more than initial kinetic energy. This happens in the situations where some of the internal energy that is stored in the particles is converting into the kinetic energy form. So the final kinetic energy will be more than the initial kinetic energy. But generally speaking, when we talk about the inelastic collisions, we'll have the Ke final will be less than Ke initial, which means some of the kinetic energy lost will be converting itself in the form of heat or deformation elastic energy or sound or light, etc., etc. Now most of the collisions that we consider between particles, like the collisions between two billiard balls or the collision between two automobiles on a road, and in general whenever we talk about the collisions, like even a ball hitting a cricket bat, we see a sound coming, and sound is a form of energy. This energy is coming due to the loss in the kinetic energy during the time of collision. So these collisions we call them as inelastic collisions, and we have an extreme case of it which we call as perfectly inelastic collision. Now the term perfectly inelastic does not mean that all the initial kinetic energy is lost. Maybe in some cases it might happen, but this generally refers to the case where the loss in kinetic energy can be as large as it can be, which means for a given collision, if we are having a situation where the kinetic energy loss is as maximum as it can be, then we'll refer to such type of collisions as inelastic collisions. And in these type of collisions, definitely the final kinetic energy will be less than the initial kinetic energy. And we have examples of this. If you have a collision between a bullet which is going and hitting a block, and after the collision we see that the bullet will be getting stuck to the block, and this is a case of perfectly inelastic collision where all the kinetic energy of the bullet will be lost. So a perfectly inelastic collision, we'll of course discuss more about it when we go into the details, is a type of inelastic collision where the energy loss is as maximum as it can be. Now the collisions can also be divided into the head-on collisions and oblique collisions. This is another classification based on the velocities of the particles. So if the velocities of the particles involved in the collision, like in the two situations that we are representing here, so we have m1 which is the first particle and m2 second particle. Here the initial velocity of the first particle, initial velocity of the second particle, they are confined to one line, and even the final velocities of the two particles v1 and v2 are also confined to the same line. In the second example that is represented here, m1 and m2, they are basically moving in such a way that they are approaching each other. So the velocities are in opposite directions, but still they are confined to a same line. Now when we talk about the one-dimensional motion, we know that in a straight line we can have two possible directions of motion. If we look at the horizontal straight line, we'll say one is towards the right, other is towards the left. So such collisions where the velocities of the particles before the collision as well as after the collision, if they are confined to one straight line, we call such collisions as head-on collisions or also one-dimensional collisions. Now the other category is like what we have over here. If the velocity of the first particle u1 and the velocity of the second particle u2, they are not along the same straight line, then we will see that during the collision the particles will be glancing through, which means after the collision what usually would happen is the particles will be moving in different directions. Now they may move in a plane which will make it a 2D type of an collision interaction, or they may even move in a space which will make it a 3D. So such collisions where the velocities of the particles before and after, they are making an angle with each other, or rather we can say the velocities are confined to a plane, or the velocities are spread in the space, we call such collisions as oblique collision. So we have the division of collisions into elastic and inelastic based on whether the kinetic energy of the particles is conserved or not. If it is conserved, we call them as elastic collisions. If it is not conserved, then we call them as inelastic collisions. And we have second classification of collisions based on the directions of the velocities. If the velocities of the particles before and after collision are confined to a straight line, then we call them as head-on collisions or also simply one-dimensional collisions. If the velocities are confined to a plane or they are confined to a 3D space, then we'll see that these collisions will be called as oblique collisions. So these are the types of collisions which can be analyzed.